For all the stuff in our world, there's a story of how it came to be.
Hello, I'm Brian Unger.
Coming up, from Main Street to Midtown, taking the fire engine to new heights. And it may be sweet, but it's not simple. Making sugar.
There is one vehicle on the road that has to run perfectly every time it leaves for its destination. And once it gets there, it's got to work perfectly every time. The fire engine. Yeah! Move over! We're making a TV show! Look out! We're at Sutphen Corporation in Central Ohio. We want to find out what makes these trucks a dependable lifesaver for the men and women who fight fires and for the people who are stuck in them. And to get the occasional cat stuck in a tree. Now, they make 3 different kinds of models of fire engines here at Sutphen. We're going to focus on 2. These big aerial platforms like this one and this one, the pumper. The first one, out of the firehouse.
Both get their start at the chassis plant in Springfield, Ohio, where they custom build an average of 200 fire engines a year.
Leroy Knupp here is the plant manager here at Sutphen. This is a pumper.
This is a pumper.
So this frame will need to support how much weight?
This one will have to support about 40,000 plus pounds.
40,000 pounds, that includes?
Water,
okay,
body, equipment, the whole 9 yards.
And for an aerial, tack on an extra 20 to 30 tons for the ladder and other parts. To carry this heavy load, Sutphen uses double steel rails attached by bolts instead of welds.
Really, when you're flying down on, say, a New York City street, these have to be able to hit those potholes, but still keep together.
Next, the axles and suspension drop in, a coat of paint goes on for corrosion protection, and our frames move on to the engine department.
Well, this is what gets you to the fire just in time. They're all diesel-powered engines, 375 to 525 horsepower, top speed 70 miles per hour, automatic transmission. Well, we put the power in the package, and now it's time to lower the cab down on this frame. Sutphen manufactures its own cabs. This is how they arrive at the chassis division, raw. These are made of aluminum. They're lightweight. They come in 8 different sizes and shapes. But they keep them lightweight so fire departments can concentrate on carrying the important stuff like personnel, firefighting equipment, and water. Now, to get this to look like this, we got to go to paint.
No one knows for sure why fire engines are painted red, but the accepted reason is obvious. They stand out.
What color is this?
Of course, not every red is created equal.
So there are 2 reds?
There's more than 2. There's probably several hundred reds. I'd hate to put a number on.
Several hundred reds?
Yeah.
A lot of cities have just their own specific, and it even goes into detail, they have their own mix and nobody else can use it.
Really? They have like patented red paints for their fire engine.
Once a fire department settles on a color, Sutphen applies 3 coats of airplane-grade paint that can withstand extreme heat, followed by a clear coat to protect against fading. When the paint dries, cabs are buffed and shined, and the interior lights and upholstery are added. The interior is designed to get firefighters to a blaze safely and quickly.
These seats right here, these have compartments that are carved out. You can put the oxygen tanks in them, secure them, so when the firefighter sits down in the chair and is taken off to go rescue someone or put out a fire, they snap in, they buckle up, and they're off.
Fully loaded, the cab finally meets its chassis.
The cabs here are so lightweight that you can literally hold them up with your finger. And a hoist.
After our cab is wired and dressed up with bumpers and trim, we have what looks like a fire engine, but it can't fight a fire. yet.
How do you turn it on?
So we'll test drive this cab to Sutphen's body plant, where cabs are fitted with pumps and ladders.
Nice.
Like the chassis, the engine body is custom designed, and it's built to hold the hoses, ladders, and other equipment. Workers stamp and shape giant sheets of aluminum into smaller pieces and then weld them together, forming equipment cabinets that will hold essential firefighting and rescue tools like hoses and the jaws of life. After the equipment cabinets meet the chassis, it's time to give our pumper a heart.
Well, if there were a beating heart in a fire engine, this would be the heart. And like a heart, a human heart, it can't fail, ever. And if it does, well, the body fails, or in this instance, the truck fails. Is that right?
Exactly.
I'm with Ken Crease here of Sutphen, and this is really what fights the fire, the centrifugal pump.
This particular pump is 1,500 gallons a minute.
1,500 gallons is about 600 times more water per minute than a typical kitchen faucet. And a pumper truck has many faucets that all need to be running simultaneously at full blast.
2 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
13 places where water is coming out of this pump?
Here's how the pumper does it. When firefighters shift the engine from drive to pump mode, a vacuum sucks water into a 12-gallon cavity. When the cavity fills, an impeller, which acts like a boat propeller, spins that water at incredible speeds. That spinning, known as centrifugal force, creates tremendous pressure, which forces the water out through the multiple valves.
How do you know this pump works when it rolls out the door?
Extensive testing.
Nearby Sutphen Pond will serve as our water source.
But right now we want to test how many gallons per minute we're spraying from this hose.
We're going to go gallons per minute and pressure.
Okay. Oh, here it goes. Is that a gauge or something?
It is. It's called a pitot gauge.
The pitot gauge measures the velocity of water. We'll run the pump for 4 hours at 1,500 gallons per minute. If the flow is constant, our pumper's good to go.
Oh, yeah. I mean, this wants to pull back on me big time. It's like wrestling a boa constrictor. Plain City, Ohio, your pumper is ready.
While the pumper is a must-have for every fire department, aerial platforms, the big boys of the firefighting world, come in handy when firefighters need to attack fires in hard-to-reach places. Both the ladder and platform are assembled here at the body plant. There's only one way to fit a 100-foot ladder on a fire truck, and that's to nest 5 25-foot ladders, one inside the other, so that they extend like a telescope. Then the ladder gets electrical wiring and 2 sets of pipes to carry water to the platform. And finally, the whole thing is attached. Now, where the ladder is mounted is the key to its stability.
Sutphen has encountered many design challenges, engineering obstacles to overcome in order to make this ladder extend perfectly every time, without fail, without collapsing, and to give the truck a sense of stability.
Sutphen installs 2 solid steel stabilizers that pop out from the sides, tripling the fire engine's footprint to an incredible 21 feet.
By positioning the area where we're doing the middle, it gives us that center of gravity, but now it allows us to rotate. As you can see, we're over top of the cab. We can rotate over top of that cab, extend all the way out, and keep the truck low enough and continue to fight fire.
So you can pull the truck right up to the fire, but pull into it head on,
right,
and extend out over it.
Right.
On one of these platforms, up to 4 firefighters with 2 hoses can attack fires from above or pull victims from a tall building without having to enter it. 4 months of assembly, and we've got a fleet of fire engines.
Don, what's the best way to handle these levers?
Ease into it until you start to move. Push it towards you for retract.
Thank you for flying Sutphen Fire Engine Airlines. All right, everybody, back to work.
Up next, burning, cutting, dumping. And that's just part of what it takes to make sugar. Flamethrowers, semis going vertical, combines that are downright scary. Just some of the tools needed to make pure white sugar.
Sugarcane. It's an incredible story that begins with burning and cutting and grinding and pulverizing and converting from solid to liquid and back again. We have many miles to travel before we get this in your coffee. I'm with Ramiro Alvarado. He's with the Rio Grande Valley Sugar Growers. This is the inside of a sugarcane stalk. Which part of this fibrous material in here is the sweetest, and where do you extract the sugar from?
Okay, everything that is inside of the casing of the cane is what we're after. And what we want to do ultimately is to extract all of the juice out of here.
To get that juice means we've got to light this field on fire. It's a controlled burn that makes for a more efficient harvest, leaving behind only cane loaded up with sugar.
Attention, attention. It's time for us to light this sugarcane field on fire. Why? Because America needs its sweet tooth satisfied.
First, we spray a fine mist of diesel around the edges of the field to be torched. The fires are lit only when the wind conditions are perfect. We need a fast fire, one that will burn up the dead leaves and only scorch the cane.
This has all been burned, and what's left is what they're harvesting with these ginormous machines. Come in here, scoop up the cane, put it in these trucks to take it to the mill. So, how do you get 30 tons of sugar cane out of the back of your truck? You do it very carefully and without being in the cab. There's a very good reason for that. 50 degrees, that's the angle at which they raise these trucks and trailers to get rid of 30,000 tons of sugar cane that's in the back.
These hydraulic systems can empty the trucks in about 4 minutes.
From here, it's loaded onto conveyors, it's washed and sent on to the hammer mill. Very impressive.
No doubt, cane is tough stuff. It's withstood flames and combines, but it's no match for the next step. Now it gets chopped to bits, washed and sent through a series of mills that crush the cane. In doing so, we are freeing the juice from the stem. The sturdy stalk is now dust, the sweet sap that will become your white sugar all wrung out. Dirt and other organic materials coloring the juice are removed at the clarification station.
That stuff's very rich, though. So what do you do with it?
All of this, as you see it coming down, is loaded into trucks, and it is recycled back into the cane fields as fertilizer.
Boiling the cane juice evaporates the water, reducing it to a syrup.
From here, all of the juice goes to what we call our boiling house. The juice is treated and then converted into sugar and molasses.
The hot solution is fed into a vacuum chamber. When the air is removed, pressure drops, prompting a chemical reaction that creates two things: molasses, that distinctive flavor we taste in brown sugar or gingerbread, and sugar crystals.
Sugar is actually a crystal. And crystals grow here for the first time.
Right. This is where the crystals are developed.
Sucrose molecules begin to bond as crystals, amassing in such volume that in a matter of hours, those crystals are visible to the naked eye.
So after these crystals have been growing for about 10 hours under pressure in these giant tanks, it's time to eyeball them. Still the one part of sugar making that can't be done any other way.
To Ignacio's trained eye, these crystals have grown to the right size, about the size of sugar crystals on your table. But anyone can see this stuff isn't even close to pure white.
So once we've judged whether we have adequate crystals, we've got to take this stuff and put it through the spin cycle.
Right.
Separate the molasses from the sucrose.
Right.
The sugar crystals are suspended in the molasses, and separating those two is the next challenge. These crystals, now 99% pure, are called raw sugar, but white sugar has to be 99.95% pure, and completely free of molasses and microscopic impurities.
I'm sitting atop 55,000 tons of sugar. There's enough sugar in this mountain, in this storage facility in Harlingen, Texas, to feed every single American 1 teaspoon of sugar. In a moment, we're going to show you how to turn that 1 teaspoon of sugar into something you can actually eat. It's on to refining.
From Harlingen, Texas, our raw, unrefined sugar takes to the sea. It's shipped here to the refinery at the port of Baltimore, Maryland. Our sugar would taste sweet enough, all right, but it is filthy. Stu Fitzgibbon runs the refinery. He knows we've got a long way to go before our sugar is 99.9% pure and pristine white.
Raw sugar has about 99% sucrose, which we call sugar, in it.
So in your refining process, you want to extract the 1% of impurities from this raw sugar.
That's right. We want pure sucrose, 99.95.
Refining to reach pure sucrose begins with removing the outer surface of the crystals. Raw sugar's brown coloration comes from a thin film of molasses on each crystal, and we have to get rid of that. First step, mix our raw sugar with a molasses-like syrup known as magma. This stuff is held over from previous batches and blended in this oversized mixer. The molasses molecules on the surface of the sugar crystals bond with the magma particles and are essentially lifted off. We'll then send our mixture into a centrifuge. The magma flies off, taking some of the molasses and a few microscopic impurities like starch with it. We're left with raw sugar liquor, a product that resembles muddy water. There is still a ton of microscopic junk in here, like bacteria, that's a real challenge to remove. So our sugar liquor moves into the ominously named saturator. 2 compounds are being injected into the washed sugar liquor, calcium hydroxide and then carbon dioxide. Their combined chemical properties initiate a reaction. As a result, crystals of calcium carbonate begin to form around any microscopic impurity. Now, it's simple. Remove those calcium carbonate crystals, and we remove the impurities. Our fourth step in the process is filtration.
And now we're in something that looks like very futuristic, very industrial. These presses, these are the Sweetland presses.
That's right.
What exactly are we doing?
Well, we form calcium carbonate crystals, and the liquid is brown. And now we need to filter that out. So this whole floor is built for the specific purpose of filtering out the calcium carbonate crystals.
These filtration presses are like massive coffee machines turned on their sides, only instead of one filter, they've got 72.
So this solution is being pressed from which end to which end?
It's actually coming up in this direction, passing through the cloth. The clear filtrate goes up through the leaf, and the cloth collects the calcium carbonate on the inside.
Our sugary sweet liquid still has a tiny trace of impurities left. We've reached the last step to clean up the sugar solution. Now we use char vessels. This is similar in concept to a water filter. Char is an absorbent, a blend of calcium phosphate and carbon. The char crystals attract the last few microscopic impurities of color molecules into ash. The result? A colorless liquid known as fine syrup. We'll run the liquid through another vacuum chamber, which results in the formation of pure white crystals. They're trapped in the final centrifuge and fed into dryers the size of locomotives.
Most importantly, we have to get the sugar in the hands of the consumer, right, Stu? I mean, without it, it'd be a very bitter world.
Well, we make it sweeter.
And you do that by having like 14 different lines up here that are packaging the sugar, right?
Yes.
Ranging from what to what?
Well, we have anything from a small sugar packet to a 2,000-pound bag.
Well, it's been quite a journey for us here in this story of sugar. Our story starting in much warmer climes, way down south, and ending up here in beautiful Baltimore at Domino's Sugar. Stu, thank you for guiding us through this. Watching sugar go from a solid to a liquid to solid, liquid to solid. To your coffee or tea, whichever you prefer.